It's a pleasure to be here at Bose Institute. So as Pratap was asking what this PVDF TRFE is, I will shortly explain what this material is. So basically this is a So first of all, I would like to thank my student Deepa, who was the main architect of this work, and Deepak Gupta, who is the co-advisor, and funding agencies like DST, etc. So let me begin by giving a short introduction to the, or short preamble to the requirement of this material. See, all of us are aware of data storage, right? We store data in mobiles, computers, etc. And there are two memories that we use typically in every device. One is the hard disk, and second is the RAM. And this RAM is basically a volatile memory. It uses a linear dielectric material like silicon oxide or tantalum oxide or hafnium silicon oxide. They are all linear dielectric materials, which means they don't have a hysteresis, but they have very high read and write speeds, which the hard disk doesn't have, and that is why you require a buffer memory to make it work faster. The problem is when the power goes off, the data is lost. So that is why, when you work on it, you have to continuously press Control S, or it has to automatically save the data every few seconds. So the solution to this problem was proposed in 1990s, that if you could make a memory out of a ferroelectric, then you have solved both the problems. Ferroelectric is inherently as fast as a linear dielectric, and not only that, so it can provide you advantage of RAM, but it can also provide you non-volatility. That is, when the power is lost, the data is not lost. So what you will have is basically a hysteresis loop, just like ferromagnetic materials show, and you will have the Boolean data storage in 1 and 0 by two polarization states of plus PR and minus PR. So this is what is the basic premise behind ferroelectric memory. It's a neat concept. A lot of work has been done on inorganic materials for storing data in thin film form, and they have made some success. There are some very good examples. For example, they have very high radiation resistance. So you cannot use magnetic materials up in space for storing data, but you can use ferroelectric materials. Another use of this particular material could be not only in the MIM form, but also as a ferroelectric field effect transistor. So you can use in the transistor design where you can have a ferroelectric just above the gate, and you can again have memory effect in the FET device, which is much more simpler than a normal memory device. So why is it useful? It is useful because you can make a simple memory. For example, you use RFID card or some smart card which needs to have a memory. Those smart cards, however, require some bending. If you keep it in a wallet, it has to fold a little bit. So which means you can't use inorganic oxides. So most of the materials that we use are typically inorganic oxides like lead zirconate titanate, strontium bismuth tantalate, bismuth titanate. They are very good materials. They have fantastic properties, but the problem with them is they are brittle, and they require very high temperature processing. So obviously with the plastic card, they are incompatible. So what we require is a new class of materials which are ferroelectric, but they are in soft state. So they are polymers basically, which should be compatible with low temperature processing, like less than 150 degrees centigrade or so that you can make plastic devices. They should be easily processable so that they can be, let's say, they can be printed. But there are some problems like, can you operate them at low voltages, because most of these devices are operated at very low voltage. Their transition temperature should be sufficiently high so that they remain ferroelectric at room temperature. They should have high fatigue endurance, because if you got to make them work for long number of cycles, they need to do that, which means they should not fatigue against many number of electric field cycles, and they should have time dependent memory retention. These are some attributes which are questionable about these materials. So typical examples of these ferroelectric polymers are this is polyvinylidene fluoride. This is PVDF in short. It's a polymer which is known for its ferroelectric behavior for a long time, but most of the times the work was done on the bulk form. Its properties can be enhanced by copolymerizing it by another polymer, TRFE, trifluoroethylene, and together they give reasonably good properties for these applications. There are some other materials like cyanopolymers, polyureas, etc., triglycerine sulfates, but PVDF is the best choice among them because of its room temperature properties. So let's just briefly look at PVDF TRFE copolymer. It has reasonably good polarization. Its polarization can touch about 10 microcoulomb per centimeter square, which is a fairly good value for a memory device. For a memory device to work at about 5 volt, you require roughly 5 microcoulomb per centimeter square as a specification. So this can store enough charge. So that's not a problem. It can be made at low temperature because its melting point is roughly 150 degrees centigrade. So as a result, it's not a problem but since we go through solution processing route, melting point really doesn't matter, but it is useful in terms of annealing. And it's non-toxic. I mean, although fluorine is there, it doesn't come out readily out of it, so it doesn't leach out, so it's in that sense, it's non-toxic. So there are 2 configurations of this PVDF polymer. There's alpha phase, there's a beta phase. Alpha phase is a configuration of trans-Gauss, and because of the angular correlation between the various bonds, the material doesn't have very large polarization. So you have one polar vector in this direction, another in this direction. They do cancel each other. So at the end of the day, you don't have enough polarization, and it's not ferroelectric also. So this is alpha phase, which is non-ferroelectric. So this is above the Curie temperature. Below the Curie temperature, you have a phase which is beta phase, which is a ferroelectric phase. It has all trans configuration, which means the angular relationships are such that you have polar vector in one direction, which is the B axis of the unit cell. As a result, this has very strong ferroelectric characteristics, and this is what we require in the device. And when you make a copolymer, the PVDF and TRFE, they merge very well with each other, and depending upon the ratios of the two, you can tune the properties and processing temperature and so on and so forth. So typically, we are using PVDF TRFE for our devices. So the design criteria for making a memory device is, first of all, the technical limitation is, you see the output signal of a memory, the current is proportional to polarization multiplied by area divided by switching time. Now in these 3 things, area is something which you cannot expand because nowadays we are miniaturizing everything. Switching time is limited by material itself. What you can change is the polarization, and polarization is dependent upon a variety of things. First of all, it depends upon the degree of crystallinity, which should be as high as possible because amorphous phases are not ferroelectric, so it has to be crystalline. So it should be as high as possible for high remnant polarization, and then the orientation of crystal, which is key. So when you're applying electric field in this direction, your polar vector should be in this direction, which means your B axis should be in this direction, which is the polar vector. So polar axis should be aligned parallel to the electrode normal or the film normal, and orientation of AC plane should be within the plane as much as possible. So this is the unit cell of PVDF TRFE. It's a fairly complex unit cell. You can see the lattice parameters 2A, 2B, 3C, and so this is the thin film configuration. You have a thin film sandwich between the 2 electrodes, and this is the applied field direction, and this is what should be the polarization direction, switching direction. So polar vector 0, 1, 0 should be along this direction, ideally speaking. When I compare PVDF with inorganic materials, there are certain issues. The issues are, if I compare various specifications like remnant polarization, leakage current, coercive field, etc., these are 2 very commonly worked upon inorganic materials, PZT, lead zirconate titanate, strontium bismuth tantalate. They have large polarization exceeding 20 microcoulomb per centimeter square in most cases, and PVDF around 8 if you take the average value in the literature or the best reported average values. And then you have leakage current. Memory should not leak the charge out, which means it should have low leakage current. The leakage current of these materials is 100 nanoamperes per centimeter square, which is very small. In case of PVDF, it can be quite high. It can be microamps, even milliamps, which is very high current, which means you're not going to have very good retention characteristics. Coercive field is the field that you apply to switch the polarization. Coercive field in case of inorganics is very low. It's less than 100 megavolt per meter. In case of PVDF, it's more than, it's up to 500 megavolt per meter, which means your operating voltage of the memory will be higher. So, and other than that, there are other parameters, but something called as read and write cycles. So you can operate these inorganics for read and write cycles up to or beyond 10 to the power 10 cycles, which is very large number of cycles. I mean, it's more than what you use. In case of PVDF, read and write cycles are not even half a year, or it's not even 10 to the power 2 or 3, very small. So these are certain issues with PVDF on which we started to work upon. Among these, fatigue is the major problem, and this talk will mainly focus on the fatigue performance and associated increase in the other properties. So these are the red boxes which show the concerns. So what we have been working on developing the flexible memories of this material, because it's a flexible material. So you can see one memory that we have developed in our lab, for example. It can be bent with your fingers easily and it works. So what you have here is a configuration. You have a PET plastic substrate on which you have deposited an electrode, which is Indian tin oxide. And then we deposit a thin film of PVDF TRFE of 200 nanometer thickness. And on that, we deposit aluminum as a top electrode. And then it becomes a MIM capacitor. And that is what we use for our device characterization. Now, when you want to work upon a flexible memory should undergoes not only it gets exposed to electrical number of cycles, but also it gets exposed to mechanical strains. So what we did was we looked at the effect of both mechanical and electrical switching on the device. So you have a configuration like that. So what we did was we wrapped the memory around a AA battery or AAA battery, which is a very large number of strain. I mean, your debit card or credit card will not flex that much. So we really flexed it completely just to look at the effect of extreme strain. And since it's a multi-layer configuration, the strain in this case, looking at the various parameters of modulus and thicknesses, strain is worked out is roughly T minus Rn divided by R plus Rn, where T is the overall thickness of the stack, R is the bending radius, and Rn is a factor which depends upon the thicknesses and moduli of the four components that I have here. So when we flex this film and measure the properties, we see that from the flat configuration to bent configuration, there is very little change in the properties of the system. The polarization, there is a bit of asymmetry which is because of different electrodes. But other than that, the hysteresis loop is of good quality. The polarization values do not change much. So if you look at this on the right side, the polarization values show very nominal change. For the PS changes from 9 to roughly 14 as a function of bending diameter, but PR remains fairly constant. And only at very extreme, only in the flat condition, there is a little change here, but not much. So it goes from like 8 to 7.5 or so. But coercivity changes. Coercivity is the voltage that you need to apply to switch it. Now, what we did was, since a memory doesn't go only one time bending, it goes multiple cycles of bending. So what we did was we did it for multiple number of cycles. So we made a homemade setup. So what we did was we fixed one end of the memory here, fixed another end here, and then rotated this motor. So it goes up and down. And we could change the distance so that the bending radius got changed. It has all been painted in pink because the girl student was working on it, so she painted it all pink. So you can see that when the bending diameter is 2.4 centimeter, 2.4 centimeter bending diameter is a very small bending diameter. It produces a strain which is far more than a device will experience in the practical life. So we switched it up to 30,000, 30 to 30,000 switching cycle, bending cycles, and the properties remain absolutely intact, which means this material can withstand 30,000 bending cycles without undergoing a degradation in the properties. However, when you apply extreme stresses going to bending diameter of 1.3 centimeter, which corresponds to certain strain, which you can calculate from that formula, there is a degradation in the properties. So you can see the hysteresis loop doesn't remain the same, and there is a bit of change in the saturation polarization and the remnant polarization. So what we see is that only at extreme strains the material degrades, but not at the moderate strain, which tells us that in the normal condition the material will remain perfectly fine for thousands of cycles. So which means it has good mechanical robustness. So what we did was we then wanted to find out the reasons, what happens. So we looked at the film under various microscopic observations. What we found that as you keep bending the film, there are certain cracks which start appearing on the surface of the electrode, which appear quickly in case of higher strains, but at much later stage in case of lower strains. What we did now, we wanted to know where these cracks are coming from. Are these cracks coming from the PVDF film, or these cracks coming from the ITO? The suspicion was towards ITO because ITO is a brittle thing. So, but what we found from this study was that mechanical fatigue is very minimal at moderate bending, and it's not catastrophic, which means you can use your device for long periods of time. So we did look at the optical images of various interlayers, and we found that cracks indeed come from the ITO, which eventually get transferred into PVDF TRFE, and as a result you have cracking at very large number of cycles at high strains. Nevertheless, what we found that mechanical strain doesn't do that much harm. But when you look at the electrical fatigue has a lot of problem. If you look at the normalized value of polarization, the normalized value of polarization drops to more than 50% after 10 to the power 3 cycles or so, which is 1000 cycles, which is not very large number of cycles. So the question was, why is this fatiguing so much? Why is that? I mean, this means I cannot use the smart card for too long a time. As far as if it has to be read more than 1000 number of times, it cannot be read. What we found interestingly was, as we fatigue, as we apply different number of cycles, the electrodes had some problems. Before the fatigue, the electrode surface was reasonably good. I mean, it was as good as you get a new electrode. But after the fatigue, it had these black pits, which means some sort of etching or some sort of corrosion or something was happening to the electrode, and we wanted to know what was happening. But before we wanted to know what was happening here, we wanted to see why does this polarization increase in the beginning and then it decrease. This was also a puzzle. So what we found here was that electrical fatigue is catastrophic and it does lead to electrode degradation. So then we wanted to explore this further. So what we did was, we first looked at the polarization increase. What we found is that when we apply electric field, after 500 cycles, the crystallinity of 110 peak, the 110 peak gets stronger, which means the material is getting more and more crystalline. So it is the field-induced recrystallization is leading to increased polarization, which is good. And we also looked at whether it's because of bending or not. We did it with bending for a large number of time, for some number of time, and then we did it with removal of bending for certain time. We found no change. So whatever the increase in polarization is happening, it's not because of bending, it's because of electric field. So that is fine. Now the question was, why does it degrade? So we found that we changed the electrode. We went from aluminum to gold, and it's still the same problem. So various questions came to mind. Is it because of oxidation of aluminum? Is it something happening inside the material? What? So when we did it with both gold and aluminum, we found that the problem remains similar. In fact, if you look at it sequentially, there is something happening interesting. You form these bubbles kind of features in the beginning, and these bubbles grow, and these bubbles become bigger and bigger, and at some places they start bursting, and wherever they look black, it's like a pit. So this gave us some idea that something is forming inside, which is sort of gaseous in nature. It's bubbling and then bursting. And this is happening, not in a very organized manner, but wherever it finds a way, it bursts. So the possibilities were oxidation of aluminum or phase decomposition. Now, if you compare this with inorganic ferroelectrics, very good work in PRL, which appeared in 2006 by Jim Scott's group, they worked on PZT, and they found that PZT also has this problem of surface degradation, that a lot of these edge pits were found on the surface of PZT. They said that this was because of change in the phase. So when you look at the Raman spectra of fatigued and unfatigued film, you see a serious degradation of the film. You see very sharp Raman peaks in case of normal PZT, but then when they were fatigued, they became very weak. What they said was, can this be recovered? So they heated the material to 600 degrees centigrade, and they saw that these Raman peaks again started appearing as a function of heating. So what they found was, when they re-annealed the sample, some of the ferroelectric properties were recovered. So they had a material degradation as a function of annealing, fatigue, but which got recovered when you re-annealed the material. So we thought, can we re-anneal PVDF? When we did that, we do not see any difference. PVDF can be annealed at only 140 degrees centigrade. So this is the degraded electrode, and this is the film. When you have degraded electrode, you have, these are the film FTIR peaks, and these peaks are not seen in the degraded film. And when you anneal them, there is no change. It remains virtually the same. So which means, unlike inorganic materials, the fatigue in this case is permanent in nature. It cannot be recovered. And the morphology also remains the same. You have the same edge pits before and after annealing. We exposed the material to electron beam, and we saw that the same bubbles were forming with the exposure to electron beam. So then we did some analysis using FTIR, and what we found was very interesting. That in the FTIR spectra of degraded spot as well as the pristine film, what we see is that there are various peaks in FTIR spectra. The key peaks are one at 885 centimeter inverse and another at 1288 centimeter inverse. One belongs to CH2, another to CF2. These CH2 and CF2 peak, they become weaker as a function of fatigue. So you can see that one at 885, another at 1288, they become absent in the fatigued film. And what we found is, what we proposed is that there is a degradation of material that is going on, which means H and F in the material, they react together to form HF. And this HF is the one which is causing the etching of the material. You know, HF is a very strong etchant. And this is what is causing HF. Vapors are basically coming out and they are degrading the whole electrode. So not only you can form HF through this reaction, but also through the reaction between the chains, and this leads to formation of a carbon bond. And this carbon bond is represented by these three peaks whose intensity increases. So what we proposed in our study was that the degradation, the fatigue in PVD-FTRF is permanent in nature. It is because of materials degradation. It is because of formation of HF by reaction that is occurring due to electric field cycling. Then the question was how to make it better. So what we thought then, we used solvents of various dipole moments. 4 minutes? Okay, I'll try to wind it up quickly. So we used solvents of different dipole moments, and we mixed. What we found is that when you use solvents of different dipole moments, you improve the properties greatly, but the roughness increases. However, the interesting thing was when you use, we were using MEK, methyl-ethyl ketone, which gave certain fatigue curve, which is a red. When we use DMSO, which is a large dipole moment solvent, we got slightly better fatigue characteristic. This gave us an idea that dipole moment of the solvent is playing some role in improving the fatigue behavior. So but DMSO increases the roughness. So we thought that let's mix these two with each other. When we mix them with each other in various proportions, what we find is that the fatigue performance of devices for certain ratio of DMSO to MEK improved greatly. There is no fatigue for two concentrations, that is for 1:1 and for 1:2 DMSO to MEK, and this is unprecedented, never reported, and we went up to, in this result I am showing up to 10⁻⁷ cycles, but we have done tests up to 10⁻⁸ cycles. There is no fatigue of this material at all up to 10⁻⁹ cycles, which is fantastic. I mean, this is very good from the perspective of a memory, and moreover, when we looked at thermal stability results, we can see that material is stable up to 380 Kelvin without degradation. 380 Kelvin is a very large temperature as far as a device is concerned, a plastic device is concerned. It's only beyond, when you go beyond its melting point, it degrades, or TC. So 380 Kelvin, it's stable, very good and used for the memory. And what we found is that the features that we saw of fatigue in pure solvents, they are absent in the co-solvent. So which means co-solvent is doing something to the film. And when we looked at the FTIR, one thing that we find is that there is a shift in the FTIR peaks, and shift in the FTIR peaks in certain direction showed us that there is a change in the bond strength. One, the bond strength increased, not too much, but a little bit. And then we did some binding energy analysis using XPS, and what we found is that when you compare the values of single solvent and double solvent, the binding energy is improved. But binding energy is not the same as the bond energy, because binding energy is based on core electrons and another is based on the valence electron. So you cannot correlate these two directly, but it has certain influence on bond strength as well. What we found interestingly was that X-ray diffraction pattern showed that the films which were co-solvent derived, they had better crystallinity. And this better crystallinity, and we did some DFT calculations as well, whose result I'm not showing you here. They all suggested that there is a better cohesion of chains, and as a result there is better chemical stability in the chains, leading to very good fatigue performance. And not only you get very good fatigue performance, you have very high piezoelectric properties here. The single solvent piezoelectric coefficient is of the order of -35-40, but co-solvent gives you piezoelectric coefficient which is 60-65, which is reasonably good for piezoelectric energy harvesting devices, along with low coercivity. The coercivity is also smaller. So overall, to conclude, I would say we found that PVD-FTRF thin films for flexible memory applications, they are not affected by mechanical fatigue, especially at moderate strains, which is the good news. What we found was electrical fatigue is a permanent effect and it is catastrophic, but it needs to be improved upon. So we developed a method which is based on understanding the dipole moment of solvent, how it affects the chain formation and crystallinity. We found that you can make fatigue-free capacitors with large piezoelectric coefficient and very good thermal stability. So thank you very much for your attention. I would be happy to answer any questions.